Hi, today I want to show you ways to improve AI applications with retrieval augmented generation. I show you different advanced techniques that you can use in combination with LangChain to get better results when retrieving data from a vector store. We will take a look at MultiQuery retrievers, contextual compression, Ensemble Retrievers, self-querying retrievers, which is my personal favorite, and time weighted VectorStore Retrivers. We first have a look at the typical workflow in an AI application. You first have the indexing step. You load raw data into memory, split the data, embed the chunks into embeddings, and store the chunks and the embeddings into a vector store. Then you've got the retrieval step. You ask a question, embed the question, and retrieve the most similar documents. You pass the documents to a prompt and send everything to an LLM, which will create a final answer. The techniques I show you are ways to improve different steps of that workflow. You can code along with me and you will find the link to the repository with the IPython notebook in the description. Okay, I'm here in VS Code, and before we start with the techniques, I show you a little experiment which shows why the chunk size matters and how you can use different chunk sizes to improve the results with a parent-child retriever. So first we have to install our dependencies. I created a requirement.txt, so we can just run pip install -r requirements.txt and install everything in a virtual environment, or if you want in the global environment. There's LangChain, there is ChromaDB and tick token, everything you need for an LLM application. Okay, let's start with setting up the OpenAI API key. We also have a pretty print docs function, which allows us to print the documents which we retrieve from the retriever a little bit nicer. And then we also create an instance of the OpenAI embeddings class. So let's run that code. In the next step, we want to load our raw data. So I provided a docs.txt and a restaurant.txt. So we will use the loader class, which is a text loader from LangChain, to load that into memory. So the importance here is the difference between docs.txt and restaurant.txt. So the docs.txt is a fictional Q&A format of a dog school, and you can ask different questions about the dog school, what's the name, where is it located, and what kind of trainings does that school offer. And in the restaurant.txt, we can see some questions about the food of the restaurant and if it's a vegan or vegetarian friendly restaurant and so on. So quite different topics. And what we're gonna do is we now load that data and do nothing with it. So we won't split it. So we have one large chunk for each of the files. Okay, now let's embed some questions. How is the weather? What is the name of the dog school? And what food do you offer? So the first question is unrelated to both files. The second is related to the docs.txt. And the third one is related to the restaurant.txt. And then we also embed all of our documents. So we've got two documents now. We can also print that. So the length of our data vector. So now we've got 3 embeddings for the questions and 2 for the files. So let's run that. As we can see, we've got 2 vectors now. Okay, now let's use that vectors to make a little plot. So we create a plot of the cosine similarity, which is a metric for calculating the similarity of different vectors, and plot that with matplotlib. So let's wait a little bit. Okay, now let's have a look at the range. On the left, we can see the queries related to the docs file. So we can see the query related docs is here on top and the others are quite low. So that's actually fine. But for the other file, we can see that the query related to restaurants, it still ranks on top, but the similarity between the first and the second, so related to dogs and the restaurant, is, it's small. The difference is very small. So if we would even cover different topics in the restaurants file, the results could be even worse. And that's why we want to create chunks to cover different topics of a single file with the embeddings. When you create an embedding over multiple topics, the result of that embedding does not make any sense. So it's quite hard to differentiate the queries against that embedding. So let's run the code again, but now we use a text splitter. So we first have to change that to data, because we will split the raw data and we will create a chunk, let's say of 120 with a chunk overlap of 10. So let's run that again. And now we will create more and different vectors. So this will not be 2. So we've got 35 vectors now. And now let's create that plot again. So we can see that the difference between the highest ranking vector and the lowest ranking vector is higher than before. So smaller chunk sizes and their vectors are therefore more selective and better suited to getting the right documents from the vector store. But on the other hand, very small chunks can provide only too little context for the LLM. And this is where the parent-child retriever comes into play. You send a query against a small, selective chunk and then send the larger document with more context to the LLM. Okay, now we have to use the ParentDocumentRetriever from LangChain to make that work. As you can see, we've got 2 splitters here. A child splitter, which will create the smaller chunks of our data. So we'll use a chunk size of 120 with a chunk overlap of 20, and then our parent splitter. This is the splitter for our larger documents. Here we can see we've got a much bigger chunk size of 400 and also a chunk overlap of 20. Then we will have to create an instance of some kind of vector store. We will use Chroma here, and then we also have to provide an in-memory store. This is where our larger chunks are stored. And then we use the ParentDocumentRetriever to create our retriever. We have to provide the vector store, and we also have to provide the document store. This is where the larger documents are stored. And then we also have to provide the splitter, the child splitter, and the parent splitter. So now let's run that code. And now we can add our documents. This is the documents we created before. So 35 documents, and we add that to our retriever. So we can just run the add documents function. To retrieve the documents, we can use the similarity search method of the vector store. So this will now return the documents. And we can also use the retriever. So this is the preferred way because it's a standardized interface for retrieving documents. This works for every retriever. So as you can see, we retrieve the same documents here. Okay, that was the parent-child retriever, which uses different chunk sizes. Now let's have a look at the MultiQueryRetriever, which uses a different approach. So why might we even want to use that MultiQueryRetriever? So when you ask a question, very small differences in the way you ask can already have a large impact on the retrieval process. So the MultiQueryRetriever creates variation of that question and uses different questions to query against the database. For the MultiQueryRetriever, we first have to create an instance of some kind of LLM class. So we use the chat-OpenAI class. Then we use the fromLLM method of the MultiQueryRetriever class to create an instance of that retriever. So we have to pass the retriever we want to have. So this is the Chroma vector store, and we use the asRetriever method on that to get our retriever. And we also pass the LLM, which we created here, to create our retriever instance. So we just have to run the getRelevantDocuments on that retriever. And as we can see, we retrieve 4 documents. So what's actually happening under the hood is that this retriever will create multiple different queries from our original question. So what is the name of the dog school? It will create variations of that and run each of that query against the database. At the end, we will create a large list of documents, and the duplicated documents which will be retrieved will be dropped. So at the end, we will end with a list of unique documents. Okay, that was easy to use, but I will actually show you what happens under the hood. We can implement something like this on our own, and the key part of that is actually a prompt template. And here we pass in a single input variable, which is question. And our prompt is that you are an AI language model assistant. Your task is to generate 5 different versions of the given user question to retrieve relevant documents from a vector store. And this is the key part. So we now will create an LLM chain. So we use the LLM chain class. LLM is not defined. So we first have to run that code again. And now let's run that again. And now we can invoke the question here. What is the name of the dog school? And the result is a list of 5 different variations of that. So here we can see, first, can you tell me the name of the dog training center? Second, what is the official name of the dog school? So this is what actually happens under the hood. So each of that questions, which will be generated by the LLM, will be now run against the vector store, and we will retrieve the documents and merge the documents into a single list of unique documents. Okay, that was the MultiQuery Retriever. And now let's have a look at contextual compression. First I will store that question inside a variable because we will use it multiple times, and yeah, we don't have to write it again every time. So what is actually contextual compression? For contextual compression, you need a basic retriever and a document compressor. And then you run a query against your base retriever. That returns documents from that retriever, and then you forward them to a compressor. So the document compressor is an LLM that takes a list of documents and shortens them by reducing the content of the documents, or is actually allowed to omit the documents altogether. So instead of passing all of the documents to the LLM to create a final answer, we make another step by reducing the content or the amount of documents you pass to the LLM. So in code, we first have to create a vector store and then add some documents to that vector store. So let's run that code. And then at the end, we also run the asRetriever method on that vector store to create our retriever object. So again, we can just run get relevant documents against that retriever, and here we can see we get 4 documents back. Okay, these are the documents we normally would pass in some kind of prompt template and pass that to the LLM. When we run a compressor, we reduce that kind of documents. So first, we have to create the compressor, and to do that, we can use the LangChain extractor class from LangChain. So this is stored in LangChain.retrievers.documentCompressors. So we create an instance of that by providing in the chat LLM class. And then we also have to use the class Contextual Compression Retriever. So we provide the base compressor object here, and we also provide our base retriever, which is the Chroma retriever here, which we created here on top. And then we just run the get relevant documents, and inside here, this will make use of the LLM chain extractor, and now we should see a reduced version of that documents here. So let's run that. So if we now take a look at the documents we retrieved, we can see the dog school is called Canine Academy, and dog 3 and 4 only contain the name. So the original question was, what is the name of the dog school? So the LLM, which takes all of the documents, now extracts the relevant information. So we don't send everything to the LLM, but only the relevant information from that question. So this makes it easier for the LLM to create a better final answer. So this is very powerful, but it's also quite expensive because you make an LLM call for every document, and an alternative which is cheaper is to use an embeddings filter. An embeddings filter won't send all of the documents to the LLM, but will send documents to an embedding model. Embedding models are cheaper and faster, so we can now calculate the cosine similarity of each document, and we can set a similarity threshold. So if the threshold is below the threshold we want to set, we can now drop the documents, but the documents will not be changed. So this only filters documents. So we have to be careful by setting that threshold. I can show you what happens if we set it quite high. Maybe we will now get an empty list. No, currently this works, but we only get 2 documents. If we set it too high, let's say 0.99, we should retrieve an empty list. If we set it too low, on the other hand, here we can see nothing is returned. If we set it too low, this won't have an impact on the documents, and we will just get back all of our 4 documents. So be careful when you use an embeddings filter. It's cheap, but it's also not as powerful as using the LLM for creating smaller documents. What is cool is that we can actually make use of multiple filters in some kind of pipeline. And as you can see here, we use the embeddings redundant filter to filter out redundant documents. And then we use another embeddings filter to filter documents by a threshold. So we retrieve documents, pass it to the first filter, then to the second filter, and then at the end, we only get the best documents for our LLM. So the documents compressor takes in a transformers argument, which is a list. And this is the sequence what we're going to do. First, we're going to use the splitter, then we use the redundant filter, and then we use the relevant documents filter, which filters by a similarity threshold. And we can just pass it here as base compressor, and then we only have to pass the retriever. And this now makes it easy to use multiple compressor steps inside the retrieval step of our vector store. So this, as you can see, this takes a little bit longer because multiple steps are required to get our documents. As you can see, we just retrieved the 4 documents. So in this case, it doesn't really matter. And yeah, be very careful when using filters. You have to know why you want to use them. Otherwise, you will make your application slower and more expensive. Okay, now let's have a look at Ensemble Retrievers. What is an Ensemble Retriever? An Ensemble Retriever makes use of multiple algorithms to retrieve the best documents from a vector store. So we can use our highly dimensional vectors with the embedding model, but we can also use another algorithm, which is the BM25 algorithm. And this is an algorithm which is good for retrieving keywords. And we can use a combination, so we can use keyword search and also vector search with highly dimensional vectors and get the best of 2 worlds. So we can use the BM25 retriever, and we can pass documents here, and then we can create another retriever and use both retrievers here inside the Ensemble Retriever. So we pass in a list of retrievers. So we pass in the BM25 retriever and also our Chroma retriever. We can also set a weights argument here, and these weights have to add up to 1. So if we set the first to 0.5 and the second to 0.5, we can say that both of the retrievers are equally important for retrieving the documents. So now let's create an instance. Okay, I can see I first have to create or install another package. So pip install rank BM25, and now we should be able to run that code. Okay, now the documents are stored in the vector store, and we create an instance of that retriever. So we can again just use the retriever interface, get relevant documents, and pass in the question here. And yeah, so this makes now use of 2 different algorithms to retrieve the best documents from the vector store. Okay, now let's have a look at the self-querying retriever. The self-querying retriever is able to use the underlying metadata of a document. So this is the document class from LangChain, and as you can see, we've got the page content. This is normally what we query against in a vector store, but the metadata is most of the time not used, but we can use it with the self-query retriever. So the interface of LangChain allows to provide these kind of additional information in the metadata, and the self-querying retriever uses an LLM to filter by that metadata. So when you ask, I want some kind of a dog school or special training for my dog, and it should be in the premium class, you can just ask for that, and the LLM will filter the relevant documents by their metadata. So this can be quite powerful if used correctly. So let's create a list of documents now. And as you can see in the metadata, we've got our type, we've got a feature, and we've got a price. This is what we want to filter. So we have to provide that information in each of our documents. Otherwise, this can lead to an error. So let's now run the code. And here you can see we also create a vector store and provide the documents we created here. Okay, now we've got our vector store, but we don't have our retriever yet. So we can use the self-query-retriever class from LangChain that is stored in langchain.retrievers.selfquery and their .base. So this is used to create an instance of that retriever. So to create a retriever, we first have to pass in the LLM, the vector store, and then also a content description. So this is just a normal string description of dog training service, for example. But the metadata field info is more important. So we have to provide the information what we actually store in our metadata. So when we scroll up here, we can see that we've got type, feature, and price. So we have to provide that information for the self-querying retriever. And we have to create a list. And inside the list, we have to create multiple attribute info instances. We have to provide the name, which is, for example, type. So as you can see here is the key of the dictionary, that is type. Then we have to provide a description. So what is the type about? So for example, the type of dog training service. And then also the type, which is just a string. So this is every time just a string. The price could be, for example, also an integer or a float, but in this case, yeah, it's also a string. So every metadata attribute info is a string. And here we can see the name is, again, here is feature and there's price. So we've got 3 attribute info instances in that class, and we have to provide that in the constructor here for the self-querying retriever. So now let's run the code, and I get an import error and I have to install lark. So pip install lark. So now let's run that. And here for the retriever, we can use the invoke method and just ask, what premium priced trainings do you offer? And here we can see these are the documents which we retrieve. So we can see this is the page content. And if we scroll to the right, we can see that we only extract documents which have got this price in the premium category. So this works very nice to retrieve the information based on its metadata. So I think that's a very, very powerful way to make the retrieval process better. Okay, so now let's have a look at a last vector store or retrieval technique, and this is the time weighted vector store retriever. This is not available for every vector store. I only was able to make that work with the Device vector store. So we first have to import some classes, and the most important class here is the time weighted vector store retriever. So what we have to do here is we have to create an instance of that index flat instance or class. So, and we have to provide the embedding size. The embedding size for OpenAI embeddings is 1536. So we have to provide that number. And then we have to use the Device class, which is just the normal vector store, provide the embeddings and provide also the index which we created here. And also we have to provide an in-memory doc store. And the in-memory doc store starts with an empty dictionary. So this is what we have to do to make that work. And then we pass in that vector store as vector store argument to the time weighted vector store retriever. And we also now have to set a decay rate. So what is the decay rate? So the time weighted vector store retriever makes use of timestamps. So you have to provide some timestamps in the metadata, and you can use, for example, last accessed at in the metadata, and this will now invalidate metadata that is not used. You can also use last created at. So last created at is responsible for, let's say, when you add documents to the retriever, and let's say, for example, you've got some news articles and you update your vector store every day. Then you can invalidate your news from yesterday just by providing here a high decay rate. So let's first start with a low decay rate and I'll show you the difference. So let's start with a decay rate near 0. And now we will create a metadata object here, last accessed at, and then set it to yesterday. So now let's add these 2 documents to the retriever. And now let's run get relevant documents and then hello world. So this should retrieve that document here. So as we can see, now we receive the document back and the page content here is hello world. So this works, but we set the decay rate to a very low number. If we set it almost to 1, then the decay rate is quite high and it will invalidate this document very fast. So this is, yeah, almost instant. As you can see, now we add the documents again, and now we can see the timestamp here is yesterday. And if we run that, we can see that yesterday is too old to retrieve that document. So we only retrieve here hello foo, even if the question was hello world. So normally we would expect to retrieve that document, but yeah, that was invalidated because our decay rate is so high. So we only retrieve the hello foo document, even it's not as similar as the hello world document. Yeah, so I think the time weighted vector store retriever can be quite powerful if you work with news articles, for example, and you don't want users to retrieve old documents, but be very careful and experiment a little bit with that decay rate. You won't or don't want to set it too high, but you also don't want to set it too low. Okay, so that's it. That were some kind of advanced retrieval techniques. I hope you liked the video, and if yes, please subscribe to my channel and like the video. Thank you very much. See you. Bye bye.